We're eager to hear what you have to say.
All right, thank you, Christian. So today I want to get started with talking about the statistical mechanics of liquid crystals. And what I have in mind here is that you guys are going to be hearing a lot about liquid crystals over the course of these 2 weeks. And I want to start off with some introductory material just to make sure that we all know what we're talking about. And so let me try to go through some of that introduction today. And of course, feel free to interrupt me at any point for questions, or to let me know if you already know everything here. The idea here, what we mean by liquid crystals, is phases with a partial order. That is to say, more order than isotropic liquids, but less order than full three-dimensional crystals. Right? So some kind of intermediate phase. So these things are typically composed of long organic molecules. Right? So the word liquid crystal doesn't refer to the material, it refers to the phase of the material. Right? But the material, a typical material of which they are composed, is this kind of long organic molecule. This specific example is what the chemists call 5-cyanobiphenyl, or 5-CB. And so this is the kind of structure that liquid crystal chemists learn how to synthesize. Now, if we want to do liquid crystal physics rather than chemistry, we typically want to go to a more coarse-grained description. That is, we want to average over all these atomic degrees of freedom. We're not going to think about where are all the atoms within this molecule. And so we will represent this by an arrow, right, indicating the orientation of the molecule. Right? There's just some unit vector in space represents which way this molecule is pointing. Okay, so now that's one molecule. Suppose we have lots of molecules. In that case, the kind of question to ask is, what's the distribution of orientations? Right? Are they all pointing in the same way, or are they all pointing in random directions in space? Now, typically, what you get is a phase where there is some orientational order, but they're not all pointing in the same direction, but rather about half of them are pointing this way and half of them are pointing that way. Okay, so they're pointing along an axis, but it's an axis going left or right, like that. Okay, so that kind of phase, where there's some statistical order along an axis, left or right, is what we call a nematic liquid crystal phase. And that's the most common kind of liquid crystal phase. Right? You might ask, why aren't they all pointing just in one direction, just pointing off to the right? Right? Well, that would be a different kind of phase. That would be something more like a ferromagnet, for those of you with solid-state physics backgrounds. That is not a common sort of phase in liquid crystals. So, since they are half pointing, approximately half pointing this way and half pointing that way, we can represent the whole orientational distribution by a big double-headed arrow like this. Okay, so that picks out the axis in space. And this axis is what's called the nematic director, represented by a unit vector n hat. Right? And you'll notice that we could equally well pick n hat as a vector pointing this way, or negative n hat as a vector pointing that way. Those are two equivalent ways of representing the same orientational distribution function, right? Because you remember that this big double-headed arrow is really representing a whole bunch of single-headed arrows, like that. Okay, so now we're partway towards a coarse-grained description. Now we want to zoom out even a little bit more, right? So it's like in Google Earth, right? You start with Stellenbosch, right? And then you zoom out, zoom out, zoom out, right? And you see all of Africa. Okay, so here in our coarse-grained description, right, we want to ask what happens to the director over long length and time scales. Okay, so over long length scales, there are a lot of regions with different orientational distributions. Okay, so they could be characterized by different directors in different positions. Right, there. Okay, so as we zoom out more and more, right, we can mathematically represent that as a director field that's a function of position and time, right? So we say a field, like an electric field or a magnetic field, right? A field means a function of position and time. And so here we see that this is a physically reasonable approximation, right? It's an approximation because the world is really made of atoms and molecules, right? And so when we say there's a field with some value, some orientation, here at a time now, right? That means that locally we're averaging over all the molecules near this position, right, at this time. Right? And that point of view, the field theory point of view, works because molecules are really, really small, right? And so that in any little local region, there are a lot of molecules. So that we're averaging over a lot of molecules just here. Okay? And so, to give typical numbers, right, if we look at a modulation like this might be a modulation taking place over microns, right? That's the sort of thing that you could see under a microscope. But the typical size of molecules is like nanometers, right? And so each region of some fraction of a micron contains 100 cubes, right, or more. So millions of molecules, right? So each of these things is some average over millions of molecules. All right. So now we could say this director could be non-uniform, dynamic, and we want to understand what's happening as it varies over space and time. All right. Now, you ask, why is this important, right? Why should we care about what the director is over space and time? Well, the main reason, the main consequence for experiments has to do with optics. Right? We want to look and see what happens when light propagates through a material like this. Okay? So here's an example of light as an electromagnetic wave that is propagating. Okay? And what you remember about light is that it has a polarization, right? That there is some electric field direction for the light, which is one of the directions perpendicular to the direction of motion, right? So in this picture, the direction of motion is going off to the right, okay, and the electric field is oscillating up and down, like that, okay? So now, suppose the light is propagating through a liquid crystal phase, pneumatic phase. Okay, well, now you have to ask, what's the orientation of the polarization compared to the orientation of the liquid crystal molecules, the director? Okay, if the light is coming in like this, okay, then the electric field is perpendicular to the director, okay? So as the electric field comes in here, it's trying to push the electrons up and down, right, perpendicular to the average orientation of the molecules, right? So it can do that some, but it's hard to push electrons perpendicular to the long axis of the molecules. You can't push them very far, okay? By comparison, if the light is coming in like this, all right, then the electric field is trying to push the electrons up and down along the long axes of the molecules, right? And so then they respond more to the electric field, right? You can induce a bigger polarization, right? So in this geometry, there's a higher polarizability, right? So a higher dielectric constant. So a higher index of refraction, right? So the index of refraction is different for light that's coming in with this orientation with respect to the director than light coming in with this polarization with respect to the director, all right? So this one is called ordinary, and this one is called extraordinary, all right? So these now have different indices of refraction. So in other words, different speeds of light, right, depending on the polarization, right, for light coming in with these different orientations with respect to the director. So that has major consequences for how, for what you see, right, when you shine light through a liquid crystal. Okay, so here's a typical example of that. Okay, so in the simplest version of a liquid crystal cell, right, we would put a nematic phase in between crossed polarizers, right? So here's the crossed polarizer and analyzer, all right? And they are perpendicular to each other. And we've got a liquid crystal in between, and now we shine light through it, right? Well, so what would happen if you didn't have a liquid crystal, right? What if it were just an ordinary isotropic fluid, right? What would you see in this case? Come on, do I need a clicker for this?
Black.
You would see black, right. You would see black. And because, right, some of the light gets polarized here, and then all the polarized light gets blocked by the perpendicular polarizer, right? But now, if there's liquid crystal in between, right, so I've shown you that there are different indices of refraction for light in the different directions, right? So the optics word for that is birefringent, right, that the liquid crystal is optically birefringent. Okay, so now if we want to keep track of what happens to the light as it's propagating through, okay, the mathematical representation of what's happening to the light is this Jones matrix approach, right? So here you have to read these equations from the bottom to the top, okay? So the light down here gets polarized by this first polarizer, okay? And so what the polarizer does to the electric field of the light is to project it along the orientation of the polarizer, right? So we could say, let's suppose that the polarizer has this orientation given by cos phi and sine phi, right, in the xy plane. So here's the electric field right after the polarizer, okay? Now it propagates through the liquid crystal, okay? So the phase advances, right, as it propagates through the material. But the phase advances by different amounts depending on the polarization, right? So for the x component, right, of the polarization, right, it advances, that's the extraordinary ray. And so the polarization advances by this amount, the e to the 2 pi I times the extraordinary index of refraction times the thickness of the cell divided by the wavelength of light. Okay? For the y component, it advances by the same kind of phase factor, but with the ordinary index of refraction. Is this clear? I see a lot of blank faces out there, and I can't tell if that's because you already know this stuff or because you have no idea what I'm talking about. Some people have no idea what I'm talking about? Yes? Okay. So the phase of light, right? So we would say, right, for any kind of electromagnetic wave, right, that you have the electric field, right, as a function of z.
I think the white chalk is probably good.
White chalk is easier to read. Okay. The electric field, right, as a function of z, right, is going to be equal to e to the I k z minus I omega t, right? That's sort of familiar from electromagnetism classes, okay? And now I just want to concentrate on the position dependence here, right? Okay, so this factor, what's the wave vector, right? The wave vector depends on the index of refraction, right? So the wave vector, let's see. So k is 2 pi over lambda times the index of refraction, right? So, and E for light is polarized along the director in the x direction. Okay. So, that's e to the I times 2 pi z over lambda and e, right, times e to the minus I omega t. Okay? Now, I want to know what that's the electric field as a function of height, z, going from the bottom to the top. Okay? So, when we get to the top, we have the electric field at z equals d. The top, right, is going to be this e to the 2 pi d over lambda and e times e to the minus I omega t. Okay? So that's this factor of how much the phase of the light has changed for light that's polarized in the x direction, because the director is in the x direction. Okay? For light that's polarized in the y direction, then you do the same thing, but the relevant index of refraction is NO. Okay? So you let the y component advance by this factor. Okay? Now you reach the analyzer. Okay? So whatever the two-component vector is, right, that represents light that's polarized, that's passed through the liquid crystal, okay? Now we let the analyzer act on that, okay, to project that along the analyzer, okay, and we get the light that's going through the analyzer up there, okay, this E3. Okay, and so now we have to do this whole series of 2x2 matrix calculations, okay, which you know, you can do by hand or you can do it in Mathematica if you're really lazy, and it works. Okay, so you can multiply those things out, and then you can say, well, what's the intensity of light? Okay, which is proportional to this E3, the electric field, right, after passing through all these stages, okay, and that works out to this expression, okay, and so it's the product of these two sine squareds, okay, and so there's one sine squared, which is pi times the thickness times delta n, the difference of these indices of refraction, divided by the wavelength, okay? and then a sine squared of 2 phi, right, where phi is the angle between the polarizers and the director. So just to make sure this is reasonable, we can check a few limiting cases. Right? One limiting case would be what happens if delta n equals 0. Right? So that's an optically isotropic material, like water, between the polarizer and the analyzer. In that case, you've got the sine squared of 0, which is 0, right? So it's black, right? That's what you guys told me before. For another limiting case, you could say, what happens if the director is parallel to the polarizer, right? Then phi equals 0, and the intensity is 0. What happens if the director is parallel to the analyzer, right? Then phi equals pi over 2, right? We've got the sine squared of pi, right? That's 0, right? In all these cases, you would see black, right? But if phi is halfway between the polarizer direction and the analyzer direction, right? Then phi is 45 degrees, pi over 4, okay? So we're looking at the sine squared of 90 degrees, and you'll have the brightest possible state. Okay? So, this is the simplest calculation, right, of how much light can get through the material, right? And this little calculation shows us, the name of the game in designing liquid crystal displays or any kind of liquid crystal devices, right? These are all situations where you either want to change the birefringence, the delta n, or change the liquid crystal orientation, phi. And if you change either of those things, you change the optical intensity, right? You change how much light gets through your device, right? And that's like the simplest possible liquid crystal display, right? Could work like that, of making something that can switch between black or shades of gray to white. Right? Then, of course, there are lots of refinements beyond that that take you into iPhones and so forth. So, that's why the orientation is important, right? That the orientation of the liquid crystal will determine how light can pass through the material and give you different optical intensities. Okay, so now, at this point, I want to concentrate on the statistical mechanics. That is, on what determines the kind of order in the liquid crystal, right? So what determines how well aligned the molecules are and which direction they're pointing, right? Or in other words, the magnitude and direction of the order, right? So I'm going to point out to you, right, that when we have the phase transition from the isotropic liquid to a nematic liquid crystal phase, that is an example of spontaneous symmetry breaking, right? That you're going from a phase that has perfect rotational symmetry, right, where all directions all around the sphere, right, are equivalent, to a phase where one axis has gotten singled out. There's one special axis, which is the director, okay? And so that is a case of spontaneous symmetry breaking, sort of analogous to the paramagnetic to ferromagnetic transition in solid-state physics. Now, in the case of a magnetic phase transition, you have an order parameter, right, which is the net magnetization, which represents what's the magnitude and direction of the symmetry breaking. Okay? So now we want to construct something analogous to that for pneumatic liquid crystals. Right? What kind of order parameter would represent the magnitude and direction of the symmetry breaking here? So, let's go back to looking at my little cartoon where there are a whole bunch of arrows which represent the orientation of a whole bunch of molecules, right? So each of them is represented by some unit vector. Let's call it a unit vector Li for molecule number I. Okay? And now if we want to know about the statistical properties of this distribution, we want to calculate the average of something. Okay? So now the question is, what do we want to calculate the average of? Okay? So, the first guess that you might have, right, if you're accustomed to magnetism, might be, let's calculate the average of all these unit vectors, right? So come on, somebody guess that. Robin, you guessed it. You're wrong! Sorry, you're wrong. You guessed wrong. Okay, so, you're wrong because it's a good guess, but this thing always averages to 0, right?
Zero.
It's 0.
Why is that wrong?
What? Well, it's wrong because it doesn't provide any information about the pneumatic phase, right? That you can see it averages to 0. The average of these vectors is approximately 0, right? Because half of them are pointing right and half of them are pointing left. Okay, and so it averages then to approximately 0. So it averages to approximately 0 in the isotropic phase, it averages to approximately 0 in the pneumatic phase, so it doesn't tell you anything about whether you're in the isotropic phase or the pneumatic phase. So, nice try, but it doesn't work. Okay, so you can say, well, the thing that went wrong with this guess was that it is odd in these vectors, right? It's the opposite when you have this vector or the negative of this vector, okay? So, instead of that, if you don't want it to average to 0, you better pick something which is even in these vectors, right? That's the same for a vector or for negative vector, okay? So, here's another guess, right? If you want something even, let's take the average of this vector dot product with itself, right? That's even. So the good news is it doesn't average to 0, right? The bad news, though, is that it's always exactly equal to 1, right? And because here's a unit vector, and so the vector dotted into itself is 1. And so you're taking the average of 1, which is 1, right? So it's not 0, but it doesn't give you any information. It's always 1, no matter what phase you're in. So, forget about that one. How about the cross product, right? You take the vector cross with itself, right? Well, that's got a problem with it. It's always 0, right? That it's exactly 0, because any vector cross product with itself is exactly 0. So you're taking the average of 0, right? So none of those things will work, okay? So here's a better idea. Instead of taking either the dot product or the cross product, you take the tensor product, like this, right? Which is also known as the outer product, or also known as the dyad, right, of these vectors, right? That is to say, it is the tensor, right, whose components are given by this, right? So it is a 3 by 3 matrix, right? So you're taking the combination of a 3 by 1 vector with itself, right? And so those things, you multiply out those components in all possible ways, right? So you get the x component times the x component. X component times y component, x component times z component, right? All those possibilities, 9 possibilities, and you just put them together into a matrix, okay? So that makes a tensor, all right? And so you can average all of those tensors, okay? okay, to get an average tensor. And that average tensor is what carries information about the nematic phase, right? It's a phase with tensor order as opposed to scalar order or vector order, okay? So I hope I've convinced you now that we don't just talk about tensor order because we want to confuse students, right? But we have to, right? It's an inherent part of describing a phase with this kind of ordering, where half the molecules are pointing this way and half the molecules are pointing that way. Okay, so this kind of average tensor would be a good representation of what is the nematic order. Okay? Now, it is sort of conventional to normalize it when we represent a nematic phase. Okay? So there's a nematic order tensor, which is conventionally written as Q alpha beta, which is 3/2 times this tensor minus 1/2 times the identity tensor. Okay? And so that is the definition of the nematic tensor order parameter. Okay? And I will show you why we do this thing with the 3/2 and the 1/2 in just a minute. Okay? So let me see. Just as a point of notation, you'll notice that here I'm using the index I to mean the molecule number, right? So I runs from 1 to 10 to the 23rd. Okay? And I'm using the Greek letters alpha and beta to represent directions in space, right? So each of those things runs from 1 to 3, right? X, Y, and Z. And so I will try to stick with that convention if I can remember. Okay. And this is a lot of mathematics, right? What clarifies the mathematics is to look at some specific cases, okay? Some particular examples, right? So let's see, for one case, let's suppose we have an isotropic phase, right? That is to say, the orientation of the molecules is equally likely to point in any direction in three-dimensional space, right? It could be X or Y or Z or any of the diagonal directions, right? So you have to average over the whole distribution of orientations, right? If you calculate that statistical average, you get 0. Okay. So this is part of the reason why people normalize this thing by subtracting off the identity matrix, the delta alpha beta, right, is to make it be 0 in the isotropic phase, okay? So this would actually be a nice homework problem. It's a homework problem, okay? So for an isotropic distribution of molecules, to calculate this Q alpha beta, right, and show that it's equal to 0. Okay. How about another case? How about if we have perfect nematic order along the z-axis? Okay. That is to say that all of the molecules are exactly aligned up or down along the z-axis. Now, so that means 50% of them are in the plus z direction, and 50% of them are in the negative z direction. Okay. In that case, we can calculate the nematic order tensor, and it comes out equal to this thing, minus a half, 1. Okay? Let me just show you how that works on the board. Can I have the lights again, please? And do we have an eraser? Yes, we have an eraser. Ah, thank you. Thank you. Okay. So, plus or minus z hat, okay? And you want to calculate this q alpha beta, all right? So that is the average of 3/2 L alpha, L beta, minus 1/2 delta alpha beta, okay? So let's look at the component z, okay? So that would be 3/2 times LZ times LZ, right? And so Z, of course, otherwise known as Z, depending on what part of the world you're in, right? Okay, so LZ is either plus or minus 1, right? So I look at plus or minus 1 squared is 1, minus 1/2 delta ZZ. So this is the Kronecker delta, right? So it's 1 if you have the same index, 0 otherwise, right? So minus 1/2 times 1. So that is 3/2 minus 1/2. It's 1, okay? What about QXX, right? Well, that would be 3/2 times LX squared, right? But LX is 0. So it's 3/2 times 0 minus 1/2 times 1. So that's negative 1/2. And that's the same for QYY, right? And if I look at it, one of the off-diagonal terms, like QXY, right? That's 3/2 times 0 minus 1/2 times 0. So it's 0, right? And the same for XZ and so forth. Okay, so this is what the tensor looks like if there's no pneumatic order. This is what the tensor looks like if there's perfect pneumatic order along the z-axis, okay? But there isn't usually perfect pneumatic order. It's usually partial pneumatic order, right? That the molecules have some distribution of orientations, that they're mostly aligned along some axis, but not perfectly. And so in that case, the Q tensor is getting reduced. It's not going to be this thing, but it's going to be this thing times some factor S, where S works out to be 3/2 times the cosine squared of theta minus 1/2, right? And so we could get that if we look at the representing the orientation in spherical coordinates, right? Can I have the light again? Thanks. If you have, the molecular orientation defined in spherical coordinates, right, with respect to the axes x, y, z, right? So here is a molecule like this, okay, with some orientation with a polar angle theta and an azimuthal angle phi, okay? Then LZ is cos theta, right? LX is, sine theta cos phi, Ly is sine theta sine phi, okay? And now Q Z Z, right, is going to be the average of 3/2 times LZ squared, right? So cosine squared theta minus a half. Okay? So this we're calling S. QXX is the average of, what is it? It's the average of 3/2 sine squared theta cos squared phi minus a half. Okay? But when we're averaging, we're looking at a statistical distribution where phi could be anything. Phi is equally likely to be anything from 0 to 2 pi. So the average of cos squared phi is going to be a half. So this is the this is going to be 3/2 average of sine squared theta times a half minus a half. Right? So 3/4 the average of sine squared theta minus a half. And when we use the fact that sine squared is 1 minus cosine squared, right, this turns into a fourth minus 3/4 average of cos squared theta. And what is that? If I did this right, it should be negative a half. Yes. Okay, so this is the interpretation of what is the nematic order tensor when you have order along the z-axis that's only partial. And how much order is there? Well, the quality of the order, the magnitude of the order, is given by this number S. So S is conventionally referred to as the scalar order parameter of the nematic phase. Right? And so it corresponds, in the magnetic analogy, with the magnitude of the magnetization. All right. What if the order is not in the z direction? What if it's in some other arbitrary direction along an arbitrary axis n? Right? Well, we can reason by analogy, right? If it were in the z direction, right, we have this factor S times this thing in terms of z, right? And S is the average of 3/2 cosine squared theta minus a half, where theta is the angle between z and each molecule. Okay? So if the order is along n, I can just take the same thing and substitute n in place of z and say, okay, well now the tensor is S times this 3/2 n alpha n beta minus a half delta alpha beta. Okay, and S is the average of this 3/2 cosine squared theta minus a half, right, where theta is the angle between n and each molecule. Right. So this is the general expression for a tensor order parameter to characterize the nematic liquid crystal. With any tensor, right, a natural way of thinking about it is by diagonalizing the tensor. Right? That is to calculate the eigenvalues and eigenvectors. And so for this tensor, we can see explicitly that the eigenvalues are S minus S over 2 and minus S over 2. Right? You could see it explicitly if you look at it in this diagonal form. Right? And so these are the eigenvalues, okay? And the eigenvectors, right? The eigenvector that corresponds to S is the director n, right? The axis along which the molecules are ordered, right? And the eigenvectors that correspond to the negative S over 2, negative S over 2, right? These are any old two vectors that are perpendicular to n. the mathematical definition of what is the director, right? That fundamentally, the pneumatic liquid crystal is characterized by this order tensor, and n is the eigenvector corresponding to the principal eigenvalue of that tensor, right? So you often will hear people saying that n is the average direction of the molecules, right? In fact, you may even hear me saying that from time to time, right? But what everybody means by that when they say it is that it is this eigenvector, right? That's what they mean by it, even if they don't know that that's what they mean by it. But that is what they mean by it, right? It's the only sort of mathematically consistent definition of what could be the liquid crystal director. Okay, so here I've been going over a lot of mathematics. Let me give you a less mathematical interpretation of the same kinds of things that we're talking about. When you look at the liquid crystal order characterized by this kind of tensor, you can see that it involves two sorts of factors, right? It involves one factor that is the magnitude of the pneumatic order, and another factor that's the direction of the pneumatic order. And these are really the two fundamental things to think about when it comes to the statistical mechanics of liquid crystals. And so you want to think about, what controls the magnitude and the direction, and what are the consequences, right? So for the magnitude, right, this is controlled mainly by changing temperature, right? That at high temperature you have an isotropic phase where the magnitude is 0. At lower temperatures there's a transition into the pneumatic phase and the magnitude is something non-zero. So this is controlled mainly by temperature, and it is important in determining what is the optical birefringence, right? That is, how different are the two different directions. So how different are NE and NO, the two indices of refraction? So at least in some approximation, the delta N in here is proportional to the pneumatic order parameter S. And so the S factor is what determines this first factor, the sine squared of this quantity in the optical transmission, okay? And then, for the direction, that is controlled by other kinds of factors, like surface anchoring and applied fields, right? Other sorts of ways that people might manipulate liquid crystal cells. And it determines the second factor in the transmitted intensity, the sine squared to phi kind of factor. So, liquid crystal science involves understanding and controlling these two things, the magnitude and the direction, right? So I would say that about 10% of liquid crystal science involves the magnitude, and about 90% of liquid crystal science involves the direction. I haven't really counted exactly. That's sort of an approximation. 10 and 9. But it's something like that. So you can see in the lectures for the rest of this winter school, if in fact it turns out to be 10% of the lectures on the magnitude and 90% on the direction. Okay, so those are ways to think about these issues, okay? And so specific questions that you might ask concerning the magnitude and direction, right? So for the magnitude, you might start with, well, how large is S on a scale of 0 to 1, right? If you know the temperature and you know the interactions between the molecules, right? How would you calculate how well ordered the liquid crystal phase is? What's that magnitude? Okay? And related to that is a question, at what temperature is the transition from the isotropic phase with S equals 0 to the pneumatic phase with S not equal to 0. Okay? So this is the subject of my lecture tomorrow. Right? This is the thing I'm going to talk about tomorrow. Then, for the direction, the kinds of questions to ask would be things like, how much free energy does it cost to change the director? Right? Or what director configuration minimizes the free energy under conflicting influences of fields, electric field, magnetic field, surface anchoring, and anything else that people might want to do to change the director. Okay? So, that leads to the very complicated textures of liquid crystals. You get very complicated configurations of the director, which can lead to very beautiful images as seen through a microscope. When we see how does the director respond to all these conflicting kinds of influences. And in particular, one kind of thing that it can do is to make defects. So here are some quick pictures of the sorts of defects that can arise in the director field. And Mark Bowick is going to talk about these in much more detail tomorrow, I understand. He's going to show you a whole topological classification of what sorts of defects might occur in the director field. But here are just some quick examples of the kind of things that you might expect to find. Right? There could be configurations where these blue double-headed arrows are rotating as you go around some central point. Okay? So this is one kind of defect. And in the topological classification, which Mark will introduce to you tomorrow, this is considered to be a topological charge of +1. Okay? The negative topological charge, -1, looks like this, right? Where the director rotates around in the opposite sense as you go about the central point. Right? And the pneumatic phase can also have half-charge defects. And so here is a half-charge defect, right, where as you rotate about the full 360 degrees around the central point, right, the director rotates around by 180. And here is the opposite of that. Okay? But as you look at these pictures, and as you look at all the pictures that Mark is going to draw for you on the board tomorrow, right, I just want you to remember that each of these blue double-headed arrows, right, represents a local orientational distribution function, right? That there are a lot of molecules, right? And so there are all these little molecules at any particular point, right, which are not double-headed arrows, right? But they have a distribution of orientation. And that distribution is what's characterized by a double-headed arrow here, right? And by a different double-headed arrow up here. Okay? And now, you might ask me, what happens at the center here, right? Where it looks like there's some kind of topological singularity, right? Mathematicians would say, there's a singularity. But in reality, there are still molecules there, but the point is that the orientational distribution function is becoming something different that's not just characterized by a double-headed arrow. For example, it might become isotropic right at the center, right? You might have the pneumatic phase melt right at the center, so that the molecules locally here are pointing in any old random direction. Okay? So, if we were looking at what is S, the magnitude of the pneumatic order, S is approximately the same everywhere except right at the center. Right? So maybe S is 0.5 everywhere, right? So 0.5 everywhere, except for some little tiny region in here, right? And then maybe S becomes 0, right, in the center, right? Or for specialists, if you know about biaxiality, maybe it becomes biaxial, right, at the center. I haven't told the rest of you about that yet. Okay, so that is about a typical configuration with defects. I can tell you more, or I can answer questions. Somebody asked me a question, or I'll threaten, I'll tell you more. Right? That's my question. Question's going to rescue you. Okay, good.
You've discussed a three-dimensional, an ordered parameter based on a three-dimensional view. And the examples you showed us, of course, necessarily two-dimensional ones. Are there any things we need to be careful of when doing that?
Well, the examples, the two-dimensional examples are just what was on that last slide with the defects, right? And so there can be defect configurations in 2 dimensions or 3 dimensions, and Mark is going to classify them all for us tomorrow, okay? And so there can be classifications of defects, right, where they all are pointing outwards about a central line, right? So they're all pointing in the XY plane, right? Or there might be a central point and they're pointing outwards in X or Y or Z or anywhere around that, right? That's called a hedgehog defect, right? Where they're pointing around. Hedgehog is a kind of animal with spikes that point out in all these directions. Also known as a porcupine, or related to a porcupine. Maybe there's a South African version. It's a porcupine. Porcupine. Okay. So in the classification of defects, right, you have to think about those three-dimensional issues, as Mark will tell you. Right? Now, you could also turn the question around and say, suppose we live in a two-dimensional universe, right, in Flatland. And maybe we want to do liquid crystal science in Flatland, right? And so in that case, we could repeat all the same stories I told you about orientational order with two-dimensional vectors instead of three-dimensional vectors. And that's fine. And so that means that the Q tensor would be a 2x2 matrix instead of a 3x3 matrix. That's fine too. We can work with that. In 2 dimensions, I wouldn't be normalizing things with the factors of 3/2 and 1/2. Right? I would pick different factors to go there so that I would still have the isotropic phase have the tensor averaging to 0, right, instead of averaging to something other than 0. But that's a very minor modification.
There must be other questions. Yeah, please.
Can you go one slide back, or this is the last slide? I find it a little bit peculiar if you look at the first one, that you say you have a singularity in the middle, right? Which could be anything, but it looks like the distribution is totally isotropic, isn't it?
The distribution is isotropic.
The distribution of your nematic, vectors or whatever you call them.
Average of the whole area.
Oh, the average over everything, right, is isotropic.
Yeah.
That's a really interesting point. I'm glad you brought that up, right? And it has to do with the length scale of the averaging, right? So, yes, if you were to average over the whole area, you would calculate 0, right? But you don't really want to do that average, right? So, and the reason that you don't want to do that average is, suppose you look at this between cross polarizers, right, under a microscope, right? What you would see, is more interesting than that, right, what you would see is that the light that passes through this little region has one brightness, right? The light passing through here has a different level of brightness, and a different there, and different there, right? And so, you know, I should have included a picture of that. But Robin will have pictures like that coming up in her presentation, right? So if you wanted to see what happens in a picture like that, right, you would say, suppose I have a polarizer in the back, a polarizer which is in this direction, right, and an analyzer which is in this direction. Okay. Then in places where the orientation is like this, right, that's phi equals 0, and so you would see dark here. Right? Up here, where phi equals pi over 4, right, you would see bright, right? So I'll draw that. You see white over here, right? Around here, where it's pi over 2, it's dark again. Right? Over here, you'll see bright again, right? Then dark, bright, dark, bright. Okay? So if you were to look at that under a microscope, you would see this kind of picture, people might call it a brush, right? Where there would be this whole pattern of bright and dark, right, going around. Okay? And so it comes from having one statistical average of the orientations around here, right, and then a different orientational distribution there and there and there, right? And so you don't even want to average over everything because you would be missing this whole structure, right? You only want to be doing a local average to see what's the local transmission of light in any particular region. Does that answer your question, or is that going off on a totally different...
No, it kind of defines the question in the sense that my doubt was actually, how should I think about the singularity in the middle? I can kind of, I don't know, I just think that I can kind of figure out what the singularities would be like in the three other cases. But in this case, it looked like if you had a point charge, that would be kind of the electric field, emanating from that point charge, just to make an analogy.
Mm-hmm.
That I can think about. In this case, would I have darkness or would I have light, for instance, in your singularity?
Right at the center, you would have dark, right? And the reason why dark, right, is that that point, right, if you could resolve it optically, which you probably can't, right, because it's too small, right? But if you could, it would be some region where the pneumatic order is getting spoiled, right, where the pneumatic order melts, because there are so many conflicting influences, right, that all these different regions are pulling the pneumatic order to align in different ways, okay? And so it gets frustrated, and it melts, okay? So it's an isotropic region, and in an isotropic region, the delta n goes to 0, right? So the two indices of refraction would be equal to each other. And so then the first factor in the optical transmission would go to 0, and so the second factor wouldn't even matter. Right? And so it would be dark for that reason. You look skeptical. Let's talk about it more maybe over lunch, which Christian is about to announce to us.
No, it's not lunchtime. It's time for our next talk.
Oh, even better. Even better. It will nourish the minds instead of the bodies. Okay.